All right, another example where we can use force analysis is circular motion. This gets tricky and messes with our intuition, so it behooves us to be careful with our language, okay? So we'll talk about circular motion. What's going on? How can we analyze it? Well, we do the same. Good news is, same old force analysis for circular motion. Now, I'd like to suggest that we be careful with our definitions. This, you will find in your reading and listening to people that they aren't always careful and they don't always mean the same thing. But I think it would be pretty easy to agree on this. The word centripetal, keep in mind, that means center, and petal means seeking. So center seeking. And if we think about that, then that means inward. In or inward. The word centrifugal means center fleeing, like a fugitive. A fugitive runs away, they're on the run, center fleeing. And so all that needs to mean is outward or out. In and out. And so if we just take those words to mean the face value, then they only specify direction, nothing else. Nothing else. Centripetal, anything centripetal means in, towards the center. Towards the center is another way, right? Centrifugal, out or away from the center. Write that down. Toward the center, away from the center. Why is that tricky? Let's take a look here. People get confused by this quite a bit. When something is moving in a circle, we talked about this was Newton's first law. Well, is that Newton's first law? Does that do that on its own? Well, let's see. If I stop having the ridge, it goes straight. And what happens is people think something's pulling it out. Oh, it's being pulled out. It's not being pulled out. In fact, it wants to go straight. You go around a corner and you fly outward and you think, oh, I've been pulled out by an outward force. Oh, it's a centrifugal force. But remember, forces are interactions. So where's the force? No, that's Newton's first law. There's no force pulling you out. That's Newton's first law. You want to go straight. You need to be pushed or pulled inward in order to turn. So that really does mess with our head. You spin this and you let it go and it flies outward. It flies outward. It go like this, right? And it flies outward. Why? Because in order for it to not go in a straight line, in order for it to turn, you have to push or pull it inward. Right? If it turns, it pushes or pulls in. So let's get some more words up here. Let's be careful. Remember that real forces, actual forces, or just forces, are interactions between two objects. Another way of saying that is you must be able to blame someone or something. Okay? So forces are strictly that. They're pushes and pulls from some other object. I call it the source on the receiver, right? That's what a force is. And if you can't blame, so what happens is we think, it looks like we see more complex situations, we think there are forces. If you can't say what object is exerting that force, then you're just imagining it, which will happen sometimes. So pseudo or fictitious forces, that's a term used not to be confused with centrifugal forces. And we'll see this, okay? So it's a term that we use sometimes, pseudo or fictitious forces. Now there's two cases here. One, either there's forces that you mistakenly thought were there, like, oh, something's pulling it out of the circle, that's why it went flying off. So avoid these. Be careful not to put those in. And you can if you can just always say what object is pushing or pulling outward. And if there isn't one, fine, but there can be outward forces. Okay? The other thing is, for more advanced work, sometimes we'll move ma over to the force side of the tracks, which is to say we know some of the forces on our receiver from other things causes that thing to accelerate. Mass of the receiver resists the acceleration. Ma is not an interaction. It is not a force. However, mathematically, you can move it over to the other side of the equation with the forces. Why would you do that? For mathematical reasons. When you get into more complex situations, you can rearrange the mathematics so it's a form that maybe you can write a computer program for, or you can use more advanced mathematical techniques to solve. Then we would call that a pseudo or fictitious force. You might have heard of the Coriolis Force, for example, as one of those things. But that's just moving it over, keeping in mind it's not actually a force. I'm just doing a math move first. So first you set it up, looking for actual forces, avoiding things that you might think are there. Okay? All you got to do is be able to make sure that you can blame an object on it. And then if you wanted to, not in this course, but later work, it gets moved over, but not to be confused with actual forces. Okay? So if it's this case, we would call it a pseudo or fictitious force. We're going to see that there can be real, actual outward forces, but sometimes there aren't. Okay? In the case where I showed you on that blue track, the object went straight, nothing pulled it out. Right? As it's going around, as you're spinning around, it feels like you're being pulled out or pushed into the side, the wall in those carnival rides, right? Nothing's pushing you out. Nothing's pulling you out in that case. There's no object pushing or pulling out. So in that case, if you're thinking of a force, but no, it's just your tendency to go straight. If you go around something and you let go, you're going to go straight. You have to be pulled or pushed in order to turn. So let's take another look at that. Everybody got that terminology, right? Center just means in. Centripetal, in. Centrifugal just means out. Now there's going to be a couple cool things here. All right. So turning, the rate at which an object turns or changes directions, right? And if you change direction, you change the velocity vector. It doesn't mean you change speed. You could be also changing speed at any instant. So notice that if the velocity is here on this curved track I have, then I move over here and the velocity is over here. So the velocity vector has changed direction. I'm not worrying about speed right now. The radius of the turn, it may not go on a complete circle, but there is a certain radius of the turn. Even at any moment, there's a radius of a turn. If it's flat, the radius is infinite. Right? If it's flat, the radius is infinite. Here's a larger radius turn, more gentle turn, and you go around that. And so the rate at which you turn, of course, if you go around a curve faster, you're going to change direction at a greater rate. So speed is a factor. If you go around a sharper turn, you will get from this direction to this direction sooner than if you go around a more rounded turn. So a greater radius means less acceleration. Okay. So the acceleration for turning, first off, is inward. It must be inward. It's impossible to accelerate outward, because all acceleration does is describe what's happening. If you turn this way, then you went from that direction to that direction. If you turn this way, then you went from this direction to that direction. And so acceleration for turning is always inward. What's another word for that? It is always centripetal. Centripetal. Inward. So acceleration is always centripetal. Okay, fine. That's the direction that the velocity vector is changing. And that just describes it. We'll see why, though. So that means that the A of turning, well, if you look at it, again, a greater speed, you're going to change direction more rapidly. A greater radius of turn, you'll change direction more slowly, right? The direction is always centripetal, inward. And so the acceleration for turning is speed squared over r, check the units. You do that. Units, make sure you do it on paper. Those units should still be in the SI MKS system, meters per second, or meters per second squared. You should be able to do it pretty quick, but do it on paper and make sure that you can prove that. So that just describes the rate at which you're turning, acceleration. Now, why do you turn? Because of forces. You accelerate because of interactions, because of forces. So the way that we do that now is to write Newton's second law. Okay, Newton's second law, we're going to look at the object, put in the forces, and one direction that's going to be really key is the radial or inward direction. Okay. So the inward direction. And so we take our forces, and these are the inward components. So the force might be directly inward entirely, or there might be a component inward. And this would be the outward components, which there can be outward forces. So this would be what direction? Centripetal. And this would be centrifugal, right? And here's the interesting thing. Acceleration's always in. So one thing you know is that the forces in always beat the forces out. That's why you turn that way. If you turn that way, that's in. If you turn that way, that's in. Whichever way you turn, the forces in that direction win the tug of war, right? So this is always more minus less. Maybe zero. There might not be any outward forces. So don't put them in there. If you're spinning something on the end of a string, then there's nothing pulling outward. This is a vertical circle, which we'll analyze, a horizontal circle, a tilted circle, but in this case I've only got a string touching it, and there's gravity. Now this gets interesting. Take a look at this. While this is swinging, let's do it in slow motion. What direction is gravity? The tension's pulling down, and gravity is down. So they're both inward or centripetal. But as I come around, and this gets complicated, so we won't really worry too much following it, the angles start changing and everything. But now at this point, the tension is up, again, inward. But relative to the circle, mg is down, out of the circle. So in this very simple case, I've got at that instant an outward, a centrifugal force of mg, and an inward force of tension at that moment. And then I go over here, and at that moment, I've got an inward or centripetal force of tension and mg. And so you just have to freeze it and look at the forces at that moment and see what's really there. But if you can't blame it on something, then there's no force. You're just thinking about, thinking there should be one. Okay, so that's how you do it. You do your old free body diagram, same old thing. Make sure you see the motion, circle, draw it down. One special case is uniform circular motion, which we mentioned, uniform circular motion. Uniform circular motion. Uniform circular means you have a constant radius throughout, and then you can track it. Uniform means you've got a constant speed. In that case, the speed is the circumference over the time to go around once, the period. You can also write that as 2 pi r times the frequency, where frequency is by definition 1 over the period. So we can play with that. And you can also write that as to 2 pi f being omega, where 2 pi f is equal to omega. We'll use that a bunch so you get used to it, so don't get overwhelmed by that. But with uniform circular motion, you have that extra added case. It doesn't mean you make a complete circle. You might make, 0.32 of a circle, or you might make 9.87 circles, revolutions, whatever the case. But still, that applies, and so that can be combined with this, where the acceleration is the speed squared over the radius of the turn, mass, and then just put it in. So here's how you do it. You go through and the keys to solving these puzzles is this. One, it's the same old free body diagram. Choose your object. Nothing changes there. You just choose your object and look for real, actual forces. Don't imagine them, right? No, don't make them up. You got to be able to blame someone, okay? Some object. Next, the coordinate system. Choose coordinate system, and one direction is going to be inward. So that you can be sure of. And that might be all you need. And then you write that equation for the inward direction. Sum of the force in, those are positive, because we're saying in is positive. Sum of the force out, treat those as negative, because the acceleration is in, as we argue. If needed, you can use the tangent, the direction tangent to the circle, which will give you the rate at which you're changing speed, because of an acceleration parallel or opposite the velocity, and the velocity is tangent to the path at every moment, this would be the rate at which you change speed. Or you may need a vertical direction as another one, and then write break your forces into each of these directions. Okay. But make sure that real forces, and then make sure you see the circle. So we're going to work on different cases. And if you don't see the circle, you may not see the actual R. You'll think something is different. R is different than it actually is. So you've got to see the circle in space. You might need to use trig or so to find that. So how are we doing on time? No? Good. Okay, so let's just do a couple of quick cases. An object like this, I've got an orange and yellow object, and they're spinning along. So if I spin along like this, if I look at yellow, it's being pulled by my yellow string, I don't know if you can see that, and the white string. So it's got two tensions on it. Those are actual forces, right? And if I do this horizontally and maybe on a surface where I balance out gravity, I don't need to worry about it so much. But in that case, this yellow object has an inward force from the white string and an outward force if it's going along in a circle from the yellow string. Which one wins? Of course, the white one does if it turns this way. So here's another case where there's an actual inward force, tension from white string, and an actual outward or centrifugal force. Here the centrifugal force, it's not fictitious, it's real. The string is pulling out. But who's winning? Of course, inward. That's why it turned that way. Now I look out here at the orange one, and that's only being pulled by the tension in the yellow string, and that's inward. So in that case, there is nothing that you can blame an outward force. There is no centrifugal force. That would be a mistake, right? So you don't put that in there. There's only a force pulling in, and that's why it turns. That's why it doesn't go straight. Right? And so there's a lot of mistakes. You go, oh, what am I feeling then? When I go around a circle and I feel like I'm being pulled out. I feel like I'm being, from what? You're not being pulled out, you're actually being pulled in. So what you feel is being pulled in. You say, oh, it's my inertia that's pulling me out. No. That's why the first law is not the law of inertia. It's not your mass that's pulling you out. It's your tendency, or your Newton's first law, that your body wants to go straight. In order to turn, you get pulled in. You get pulled inward. You want to go straight, but when we see things going around, it messes with our perception. You want to go straight, right? If I go like this is a nice case here, and I swing it around, maybe you can see the orange better, I don't know. But like, that's interesting. Do you see the circle? The circle is horizontal, as best I can. It's not the length of the string that's the radius. I have to use the length of the string, that angle, draw it really quickly. In that case, I've got a string, some length L, going at some angle theta, and going around. Now I see the circle, and this is the radius, which is L, just look at the trigonometry, sine theta. Right? And that's H. So anyway, do it, we'll work some more.